Today we're going to talk about section 9.3, answering questions about the mean of a population. And what we're going to look at in this section for the most part is we are going to look at confidence intervals. Right, so between chapter 7, between chapter 8, we talked about confidence intervals and hypothesis testing. Right, in chapter 7, when we were talking about confidence intervals, we used our confidence intervals to make guesses about a range of values. So in this section, we're going to do the same thing. We're going to use the same technique that we saw in chapter 7 to make inferences about the means of our populations. We're going to construct and interpret confidence intervals for these population means. So to just kind of review, we talked a little bit about this in chapter 8 as well. When we're thinking about these different types of problems that we've seen in the last two chapters, we've had two main different types of answering questions. Confidence intervals are used for estimating parameter values, and hypothesis tests are used to decide between values for a parameter. So in some cases we can use either method to answer a question, but only thing that's really changing, these methods aren't going to change. We're just going to slightly change different pieces of our approach because we're dealing with sample means instead of sample proportions. All right, so we're going to use our confidence interval to estimate things about our population mean. Again, it's going to provide us a range of plausible values. So instead of getting a range of percentages like we did before, we're going to get a range of values that could possibly be where our mean lands. We also have a confidence level. So the confidence level is the uncertainty that's in our problems. That's going to be the same. We're going to see the same type of things that we did back in chapter 7. When to use a confidence interval? We want to use confidence intervals when we are estimating the value of a proportion. We do not use confidence intervals if there's no uncertainty in our estimate. So if we already have information about our population, we don't necessarily want to use our confidence intervals. Interpretations of confidence intervals. Remember that our interpretation should include the confidence level, the population that's in question, and our range. Again, our confidence level is a measure of how well the method used provides the confidence interval, or how well the method used to produce the confidence interval performs. For example, a 95% confidence interval means that if we were to take a random sample of the same size from the same population, 95% of them would contain our population parameter. Right, so not really anything new here, just kind of a review or summary of some of the different things that we saw towards the end of chapter 7, in section 7.4 and a little bit in section 7.5. All right, so our first example is a confidence interval appropriate. A used car website wanted to estimate the mean price of a 2012 Nissan Altima. The site gathered data on a random sample of 30 such cars and found a sample mean of $16,610 and a sample standard deviation of $2,736. The 95% confidence interval for the mean cost of this model car based on this data is $15,588, $17,632. All of these values are probably a little bit high. It's been a while since I've switched the actual data for the problems, but we're just going to go based on the numbers that we're given here. Right? Describe the population. Right? Is the number 16,610 an example of a parameter or a statistic? Right? So thinking about this, we're asked a couple of different things here. So the first thing we're asked is to describe the population. Right? Our population, remember, is going to include the word all. Right? So we're going to say the population is all 2012 Nissan Altimas that are for sale. Right? Is the number 16,610 an example of a parameter or a statistic? Right? We are looking at the 16,610 as a sample mean. Right? So the 16,610 is a statistic because it is the measure of of a sample. Right, so again, just a reminder, population means all. Right? Population goes with the word all, and statistics go with the idea of a sample. Right? Verify the conditions for a valid confidence interval are met. Right? So our sample is random and independent. We are going to assume so. Right? We have a random sample of 30 cars. A large enough sample. We don't know our shape. Right? Our shape is unknown, but our sample size is 30, right? Which is greater than or equal to 25. Right? A large population, we're going to assume that there are more than 300 Nissan Altimas from the year 2012. So we're going to assume that our population is large enough as well. Right, now we're asked to interpret our confidence interval. Right, so the last line of our problem says the 95% confidence interval for the mean cost of this model car based on this data is $15,588 to $17,632. So again, when we're interpreting our confidence levels, remember we start with our confidence level. So we are 95% confident that, right, what are we talking about? We are talking about the mean cost of a 2012 Nissan Altima. Right, and then we're going to talk about our range is between $15,558 and $17,632. So again, good interpretations contain three things: our confidence level, what we're talking about, right? So the population parameter in question, right? The mean of our 2012 Nissan Altimas, and then the range of values, so the values that it's in between. All right. So we're going to talk a little bit about finding our confidence intervals. So as we're going through and finding our confidence intervals, our first step, just like we saw in section 7.4, check our conditions. Our second step, just like we saw in section 7.4, find our standard error. The only difference is we have a different standard error formula than we had in chapter 7. Right? Find the standard error estimate. Again, it's an estimate because we're using this estimation to guess for our confidence interval. Find the margin of error. Back in section 7.4, we took a z-star value times our standard error. In this particular chapter, because we're dealing with sample means, we're going to use something called a t-star value, which we'll talk a little bit about on the next page. In this particular case, to save a little bit of time, we're not necessarily going to worry too much about our t-star value, finding that and calculating that. Just know that it's kind of similar to our idea before, but it's based on a slightly different distribution, which again, we'll talk a little bit about that distribution. But instead of going through and doing these calculations by hand, like we did in section 7.4, we're just going to rely on technology to find this. So we're just going to be using StatCrunch to find our margin of error and then to find our interval. Then our confidence intervals themselves, instead of being a p-hat plus or minus m, right, since we're estimating things about our mean, we're going to use an x bar plus or minus m. All right, so before we get into too far into our process for finding our confidence intervals, again, we're not going to do a lot talking about our t-distribution, but there are just a few things to mention about our slight differences from chapter 7. Instead of using a z value here, we're going to use a t value. And so we're going to be using a t value to find our confidence intervals. This entire page of notes has to do with different things about our t interval and our t statistic. So our t statistic is very similar to our z statistic. We're taking an observed value minus a mean, and then we're going to divide it by our standard error. But because our standard error changes so much based on our sample size, then our t statistic is a little bit more variable than our z. Right? It doesn't follow exactly a normal distribution, but it is close enough that if our conditions hold, we can use a t distribution to find our use our central limit theorem and find these different probabilities, and then in turn find our different confidence intervals. Our t distribution, right, what we're going to kind of focus on here is this middle paragraph. It is symmetric and unimodal like our normal curve. The only difference is it has slightly thicker tails. Our shape depends on our degrees of freedom. Our degrees of freedom are related to our sample size. Our degrees of freedom is our sample size minus 1. So when we see degrees of freedom, that's what that is referring to. If our degrees of freedom are small, the tails are thick. As the degrees of freedom increases, our tails get thinner. And we're going to look at the couple of images down at the bottom of this page to show what we mean by the first statement and this statement here. Because of the thicker tails, it is more likely we will see extreme values than it is in a normal distribution. So looking at these images at the bottom and kind of summarizing the information that's on this page. Our t distribution is very similar to our z distribution, but not exactly the same. We're not exactly normal. So what we see here is we see a normal curve, our standard normal curve, and then our ones with our degrees of freedom. Notice that the tails, these pieces on the end, are a little bit thicker. Right? So looking at this, a t distribution has slightly thicker tails than a normal z distribution does. But as our sample size gets bigger, right, as our degrees of freedom get bigger, which is connected to our sample size, right, what we're going to see is that this curve goes from something that's different than our normal curve to something that's almost identical. Right? So like we did in the other sections, like we saw in the other sections, right, we definitely need to be aware and be thinking about our sample size. The larger the sample we have, right, the more precise our estimation is going to be. As far as doing calculations, again, we're not necessarily going to do a lot of calculations to find our t statistic and t star value. Instead, we're just going to kind of use the idea that we're similar to our normal z distribution. We're just not exactly the same. Okay. All right, so when we are finding our confidence interval, we're going to need 4 different pieces of information. Our x bar, our sample mean, our sample standard deviation, our s, and our sample size, our n. That's going to be what is going to be required for us to use in StatCrunch. The last thing, this multiplier t star, we can look up in a table or use technology. Again, because we're using StatCrunch, we're not going to worry too much about this last value. So our focus, right, as we're going through these problems is these first 3 values. Right? We need to make sure we have a sample mean, a sample standard deviation, and a sample size. Right? Then we're going to go into StatCrunch, and we're going to do, again, something very, very similar to what we've done before, but in section 9.3 and 9.4, we're going to use a slightly different test for these. So we're going to find our confidence interval, and there is one typo here. This should say for the population mean. Okay. So what we're going to do, we're going to go to stat. We're going to select, instead of z stats like we have before, we're going to select the one that says t stats. So the only big difference as far as our selection goes is we're going to pick t instead of z. Just like we did before, we're going to select one sample with summary. Right? So we're going to, again, just slightly pick a different test than we previously used. We're going to enter those 3 values that were listed at the top of the page. We're going to enter our sample mean, our sample standard deviation, and our sample size. Then we're going to select confidence interval, make sure we have the correct confidence level that's in there, and then select compute. Right? So not any more difficult than what we saw in Chapter 7, just a slightly different choice in our menu that we're going to be looking at. All right, so we're going to go through 2 different examples. Again, I'm going to kind of explain what we want to put in as we're going through and thinking about StatCrunch. And then I will put a PDF file with our instructions for StatCrunch up online as well. So for example 3 in this section, data on the speed in miles per hour for a random sample of 30 cars traveling on a highway was collected. The mean speed was 63.3 miles per hour with a standard deviation of 5.23 miles per hour. Find a 95% confidence interval for the mean speed of all cars traveling on the highway. Verify that the necessary conditions hold. Interpret the interval. Is it plausible that the mean speed of cars on the highway is 67 miles per hour? Why or why not? All right, so we're going to start out listing the information that we have and then go from there. So our population is going to be all cars on the highway. Okay. Our sample size, right? 30 right, cars were sampled. All right. Out of this sample, right, our X bar is 63.3. Right? That was our mean from our sample. And our standard deviation was 5.23. There's our S. Degrees of freedom. Right? Degrees of freedom, we're not going to have to worry too much about. If we were going through and doing these by hand using a table, we would need this, but just to kind of review what this means, our degrees of freedom is our sample size minus 1. So our sample size is 30. 30 minus 1 gives us 29. Our confidence level is 95%. Right? And then what we're looking for, what we want to know, we want to know our confidence interval, right, which is going to be X bar plus or minus M. Right? Then once we know that interval, right, we're also asked about 67 miles per hour. So we're also going to say, is 67 miles per hour in our interval? Right? So we have a two-part question here that we're looking at. All right, step 1, check our conditions of our central limit theorem. In all reality, our first condition, sampling is random and independent, always holds. Our last condition, our population is large enough, always holds. All right, so what we really need to do is look at our sample size. Well, our sample size is larger than 25, right? Our sample size is 30. So we're going to skip, we're going to assume all of these are met. We're not actually going to go through and write out everything, right? But our sample size is larger than 25, so we know we're good. All right, we're going to find our standard error. So our standard error, again, we take our S divided by our square root of N. Right? So 5.23 is our standard deviation divided by our square root of 30, which is our N, and it gives us 0.955. Now we're going to find and interpret our interval. Again, we're not going to separately find our margin of error here. We're going to jump to StatCrunch. And what we're going to do, again, is we're going to use our T-stats, right? So instead of using Z-stats, we're going to use T-stats. And then we are going to enter, right, looking back up at our problem, we are going to enter our N, our X bar, and our S. Right? So then we're going to use N, X bar, and S. Right? We make sure we select the appropriate confidence level. So in this case, we have a 95% confidence level. And then that's going to give us 61.35 to 65.25. Okay. All right, so there is our confidence interval. All right, so our interpretation, right? We are 95% confident that the mean speed of cars on the highway is between 61.35 miles per hour and 65.25 miles per hour. Okay. Right, so we are 95% confident that the mean speed of cars on the highway is between 61.35 and 65.25. Again, we're going into our T-stats. Right, one sample with summary. We enter our mean, our standard deviation, and our sample size. Make sure you're getting the appropriate values in the appropriate spots. Okay. All right, now we're going to answer the question, is it plausible that the mean speed of the cars is 67 miles per hour? Why or why not? Remember, as we're answering these types of questions, we want to look and see if the value in question is within our interval. Our interval goes from 61.35 to 65.25. Right, so we are going to answer no. Right. Since 67 miles per hour is not in our interval, it is not plausible. That is not a plausible value for the mean speed of the cars on the highway. Okay. Right. Oops. I think I cut off a little bit. All right. So again, we start by listing everything that we know. Our conditions, our sample size is really the only thing we need to pay attention to. Right. That's larger than 25, so we're good. So we just kind of skipped them, assume they were met. Right. Standard error we find by taking our s divided by our square root of n. Then we found our interval using StatCrunch. Again, we're using our t statistics because we're thinking about a t distribution here. Right, so we are 95% confident that the mean speed is between 61.35 and 65.25, and 67 was not in that interval, so it's not a plausible value. All right, so we'll work through one more problem from beginning to end, and then answer a couple of questions about that as well. Right, so a random sample of 35 college students was asked how many movies they had seen in the last month. The sample mean was 4.14 movies with a standard deviation of 10.02. Constructed 90% confidence interval for the mean number of movies college students see per month. All right, so we're going to start with our population. Our N is all college students. Our sample size, 35 students sampled. Right. Out of this sample, our mean was 4.14 movies. Our standard deviation, 10.02 movies. Our degrees of freedom, remember it's our sample size minus 1, so our degrees of freedom is 34. Our confidence level, we are told in this one, is 90%. Right? And what we want to know the confidence interval, which again is our sample mean, our x bar, plus or minus our margin of error. Right. Again, we're going to skip all of our conditions. Our sample size is larger than 25, so we're going to assume that we're good. We're going to find our standard error. So our standard error, 10.02, because that's our standard deviation, divided by the square root of 35, gives us 1.694. Right. And then we're going to go to StatCrunch. We're going to go to T-stat. Right, and we're going to use the information from above. Right, we're going to use our x bar, our s, and our n. Right, that's going to give us an interval of 1.28 to 7.00. Okay. All right, so we are going to say we are 90% confident that the mean number of movies Right, seen by college students in a month. Is between 1.28 and 7.00 movies. All right, so between about 1 and 7 movies. All right, now we're asked a couple more questions here. All right, if we were to use the data to construct a 95% confidence interval, would the interval be wider or narrower than the 90% confidence interval? Why? All right, we're going to say a 95% confidence interval would be wider because it would have a larger margin of error. Right. As the confidence level increases, so does the width of the interval. We saw an example kind of going through this back in section 7.4 that kind of showed if you want to test it on your own, if we were to re-enter and put in a 95% confidence level instead of a 90%, we would end up with a larger range in this case. Right. Then the last question down at the bottom, what would be the effect of taking a larger sample on the width of the interval? Right. If we take a larger sample, right. Larger sample means the standard error would be smaller. So if we take a larger sample, the standard error would be smaller. Right. This means the margin of error would be smaller. And so the interval would also be smaller. Okay. Right, so these last couple of questions just kind of give us more detail about if we were to make some changes in our problem. If we were to increase our level of confidence, our interval gets bigger. If we increase the size of our sample, our interval is going to get smaller. Right? So as you're working through the ones in section 9.3, again, we're not focusing too much on our calculations with our t-distribution. Just be aware that we are using a t-distribution in our t-statistics test in StatCrunch, not our z-statistics test. And then as we're going through looking at these problems, you want to get comfortable finding your standard error, finding and interpreting your confidence intervals, and thinking about what would happen if you change some different values in your problem.